The integration of tangent to the m of x, secant to the n of x, when actually both powers are actually even. Okay, so when both powers are actually even. So what if we wanted to take the integral of tangent squared of x, secant squared of x dx? Okay, what I want you to know is that for these problems we use u substitution. Okay, some will require that we actually will change the integral to one whole different thing, and then we use u substitution. So that will require an extra step. But for the most part, it's u substitution, and we're going to go through a problem that illustrates what I just said, so we can better understand it. So again, when both parts are odd, the integrations are actually not too bad. And so if I look at this, if I set u to be tangent and I have its derivative, okay, so in this case, if I set u to be tangent of x, then my du is actually secant squared of x dx. And so I could rewrite this integral as u squared du, and the integral is given by 1/3. What was my u? Tangent of x as a tangent cube of x plus c. Okay. Now, what if we wanted to take the integral of tangent squared of x secant to the fourth of x dx? How would we do it? Well, again, I'm always going to look for u substitution. Notice if I set my u to be tangent of x, the derivative is actually secant squared of x. I have 4 secants here, so that would not work. That doesn't make any sense. Okay, so if it's not a u substitution right away, our second line of defense, now becomes to split this secant here, because we have its derivative. We have secant squared of x, which is the derivative of tangent. Okay, so in this case, we're just going to borrow 2 from a tangent, and we're going to split it up. So this becomes tangent squared of x times secant squared of x times secant squared of x dx. And the reason why I split it up is that notice that if I set u to be tangent of x, I have its derivative, which is secant squared of x. However, I have an extra secant squared of x here, which I don't need. Well, how could we get rid of it? Identity, okay? And so we know this is the integral of tangent squared of x times, so what's the identity of secant squared of x? Well, that's just tangent squared of x plus 1, and that's being multiplied by secant squared of x dx, okay? Notice that now if I distribute, and there's my equal signs, if I distribute, this now becomes same base, I just add my exponents, this becomes tangent to the fourth of x plus tangent squared of x, and we're going to multiply that by secant squared of x dx. Okay, in this case now, if I set my u to be tangent of x, and my derivative is actually secant squared of x dx, which is exactly what I have here. And so the integral is now be given by u to the fourth plus u squared du. Okay, du represents secant squared of x, and our u is tangent, but it's just u raised to the fourth, u raised to the second power. And so if I take the integral of this becomes 1/5. The integral is going to be given by 1/5. What was my u? That has to be tangent, so that'd be tangent to the fifth of x. Okay, plus 1/3 tangent to the cube of x plus c. Okay, and this will be my integral. So again, notice that this requires an extra step, but the idea stays the same. For this one, it was just straightforward. For this one, we had to split, and I had to split the integral of secant squared of x to use one as the identity and keep one out to stay as my derivative. Okay, and so that's the general idea behind when both powers are actually even.